Hello, students. Couple questions out of 13.3, section B. Got some homework and some MCs here. Let's take a look. First one was on 2 part C, and it does say use the Pythagorean theorem to find x. So if you look at where x is in the picture, the x is on the base of the square pyramid. So probably, like if I was doing this one, I might just say, hold on a second here. Basically, I just have a square. And I know that the side length here is 4. And I want to know, well, I mean, you could think, hey, wouldn't it be great if they asked me to find how long it is, like across here, because you know it's a square. And they're kind of asking that, but instead they're saying, hold on, not that. Cut that in half, and that's the piece that I want. So if you look here, X is really this kind of half piece right here. So I still would go through and find the whole length, and then you can just cut it in half because that's kind of what we're doing. So that would be the idea there. And again, you know this is a square because it says it's a right square pyramid, which means you know both sides have to be 4. You could use the Pythagorean theorem to find the hypotenuse. Okay, so that takes care of C, and let's jump over to E. Yeah, this one is going between multiple planes, so not quite as quick as the last one, but we could still use the same idea. And so if we took a picture of a square like this, we could find, and again, this square, by the way, is a 3 and a 3, because that's what it says. It's a cube. Start with the square. Go with just the 2 dimensions, and then go through and find the length right here. Find that diagonal. And you can use the Pythagorean theorem to find that. What you just found is the diagonal that goes across the base. So now that diagonal that you just created, that becomes one of the legs of your next right triangle. Your next right triangle goes over, and then it goes up, and the up part, I'm trying to change color here to make it match what we had before. The up part is, once again, 3. So that's, I'll put a 3 up here on the grid. It's that back one that's going up. Okay, so it's right here in the picture. And then you've got this diagonal that comes through the middle. This is the first time it's come through the middle of the 3-dimensional shape. And there it is. And so now you need that right to there. So this kind of brownish mustardy color here is that diagonal. Find the diagonal right there. Find that diagonal's length. Put it down here into this picture. Use the Pythagorean theorem one more time, and you will have solved for what is the length of the diagonal of a cube. Very cool. All right, let's take a look. What else? 17. Let's see here. Show how the figure can be used to prove the Pythagorean theorem. Now, I did put this in the video for the homework, so I recommend taking a look at that. And let's see. Yeah, I think I would probably, yeah, I still think that I would probably do very similar to what I would do in that video, which is first you have to prove that what you have is a square on the outside. You know it's a square on the inside, okay, because you can see all the right angles. So those are the right triangles. You need to prove that this is a square. And I know you can do it. Think about this. You have 4 triangles here that are identical. You have triangle 1, 2, 3, and 4. Okay, so you have 1, 2, 3, and 4. Now, with 1, 2, 3, and 4, they're all the same. Notice they're sides of A and B with the third side of C. And so I would recommend if you want to prove that this is indeed a square, you'd have to say, well, maybe call this angle. That's the angle between A and C. Call that some number, your choice, or call it some variable like X or something like that. I'll just call it red for now. And then pick another one for the one next to it. The one next to it here is green, which means this one over here is green, which means this one down here is green. So that's kind of the idea. And now, can you guarantee that up here, what I see in this corner is actually that a green plus a red has to equal 90 degrees? That's what you'll have to show. All right. And I think that I would say that about does it, because what you'll really say is what you're going to do is look at the area of the square in two different ways. One of them being it's a square with a side length of C, and so the area of that is C times C. And then the other one is going to be break the area inside up into 5 pieces and simply say that it's 1 plus 2 plus 3 plus 4 plus 5, which is the square in the middle. And take a look at that. And if you can do that, then you can say, well, the area of the square didn't change, so it's C squared, and the area of the stuff inside is the same, so it's this other thing. And you'll be able to kind of, I think if you multiply this out, some of those pieces will disappear because of the distributive property. And you get to kind of watch that happen. So there we go. That's question 17. There's my push in the right direction on that one. What else do we have? MC 13, and I think MC 13 is the one that I just did in that other video. So take a look in the other video that I made, because I did do this exact one, kind of walk you through it. Again, that scaling up of linear to area measures are really good. And never take a look here in MC 16. So MC 16 is very interesting. It's talking about, and again, this was in one of the videos I made for the class where I kind of demonstrated it using GeoGebra. And the idea is similar, think about how similar polygons are constructed. Similar polygons have to have the proportional ratios of sides. And so if they're proportional, when you scale them up to areas, you are simply squaring them. So the sum of those acts exactly the same way that it does with the Pythagorean theorem. So that's kind of the big picture, not really the hidden mystery, if you will, but kind of how we handle things in mathematics is to just kind of say, we now know the linear measures are proportionate. So that means the measures of everything else, the squares would be in proportion in a sense. So that's kind of the idea. And that's why it always works. Because if it works for squares, then when you go to other shapes, again, the reason it works for squares is all squares turn out to be similar. So if you use other shapes, as long as they're similar to each other, you can get there just fine, same exact way. So it's very cool. It's a really cool technique. Yes, that means half circles would work just fine, kind of like the image over here in MC number 7. There's half circles on the sides. So that would actually work too. All right. Well, that wraps it up for these. Hope that helps. Let me know if you need anything else. Off you go.